Hello, everyone, and thanks for coming to my talk. The title of my talk is Finite-Time Stabilization of Switch Systems with Unstable Modes. And this is the joint work done under the supervision of my advisor, Dimitra Panagu from University of Michigan. So this is the outline of my talk. I'll start with introducing the notion of finite time stability. Then I'll motivate the problem that we study in this work and present our contributions with respect to the prior literature. Then I'll present the main results on finite time stability of switch systems. And then finally, I'll conclude my talk with some thoughts for future work. So as we all are aware, the notions of asymptotic and exponential stability require that the system trajectory converge to the equilibrium point as time tends to infinity. In contrast to that, the notion of finite time stability requires that the same thing happens, the convergence, within a finite amount of time. So instead of as t tends to infinity, we require that the convergence happens as t tends to some capital T. This was formalized by the authors of the paper given below. So consider a nonlinear system and assume that the origin is the equilibrium point. The authors defined the finite time stability as follows. So the equilibrium point, or the origin in this case, is called as finite time stable equilibrium point if it is Lyapunov stable and there exists a settling time function which takes finite values such that as t tends to this capital T, the system trajectories reach the origin. Now, the authors also provided Lyapunov conditions for assessing whether the equilibrium point is indeed finite time stable for this nonlinear system. So they present that if there exists a positive definite continuously differentiable function whose time derivative along the system trajectories satisfy this kind of an inequality, then the origin is indeed finite time stable, and they also give an upper bound on the settling time function. So the system trajectories are guaranteed to reach the equilibrium point starting from some x naught within this much amount of time. In this paper, we study finite time stability of switch system using multiple Lyapunov functions, and we allow the system to have unstable modes. The prior work on finite time stability of switch system use common Lyapunov function, which means that the Lyapunov function must keep decreasing along any of the modes, and thus they do not allow unstable modes to be present. Now, why do we care about unstable modes? So there are a lot of applications where either the switching law is not under user's control and the system might switch automatically to an unstable mode, or keeping the system in the finite time stable mode at all times might lead to undesirable behavior. So as an example, consider a spacecraft problem which is required to track a desired trajectory. The figure here depicts a particular instance of this problem where the spacecraft is trying to track a desired trajectory so that it can observe the point of interest on this asteroid. And the battery level of this particular spacecraft can be modeled as a switch system where it increases to its fullest within a finite amount of time when the solar panels points in a particular direction towards the sun, and it decreases when it's not pointing towards the sun and when the spacecraft is tracking its desired trajectory, pointing towards the point of interest using its communication and control systems. So in this particular example, if we keep the finite time stable mode active, which is the mode when the solar panels are pointing towards the sun at all times, then it would lead to worse tracking performance. So the prior work on continuous time system, that there has been a lot of work guaranteeing equilibrium point of a continuous time system to be finite time stable for hybrid and switch systems. There has been some work on finite time stability using the notions of common Lyapunov functions and other notions, including making assumptions that the system dynamics are homogeneous. Well, in this paper, what we do is we utilize this prior work on stability of switch system using multiple Lyapunov function, and we modify these conditions to guarantee finite time stability of switch systems using multiple Lyapunov functions. So in that, what we do is we allow the system to have unstable modes. And in addition, we also present a switching signal design such that the resulting switch system would have its equilibrium point as finite time stable. So this is the system dynamics that we consider. The right-hand side of the system dynamics is allowed to switch between n modes, and we make this particular assumption on the solutions of the system. So we assume that the solution exists. It is non-zero, which means that there cannot be infinite number of jumps between the system dynamics in a finite amount of time, and that the solution is complete. In addition, we also assume that there is a non-zero dwell time for the finite time stable mode, which means that whenever the finite time stable mode gets activated, it remains activated for at least this duration TD. And we do not need to know this TD for our results, but we only need that this T subscript D exists and it's non-zero. So under this particular assumption, we present these conditions guaranteeing finite time stability of the equilibrium point. So essentially, under these four conditions, we prove in a paper that the origin of the switch system presented on the previous slide will be finite time stable. And I'm going to present all these conditions, or rather explain them in detail on the next slide. So in the first condition, what we are doing is we are allowing the consecutive Lyapunov functions at the switching instance to increase as long as their increment is bounded. In the second condition, we are allowing the Lyapunov functions along a particular mode to increase, again, as long as its increment is bounded. So due to condition 2, we allow unstable modes to be present in our switch system. In condition 3, all we require is that there exists one mode which is finite time stable, and its Lyapunov function satisfies the condition given on the right, which is the traditional continuous time finite time stability condition. Finally, the most important condition is the fourth condition, which requires that the finite time stable mode gets activated for a minimum accumulated time. So we do not require this finite time stable mode to be activated for a long time in just one activation period, but even if it gets activated, say, m number of times, its total time of activation should be at least this much amount given on the equation on the right. So under these four conditions, we show in the paper that the equilibrium point would indeed be finite time stable. Now, in addition, we also present a switching law design, which is based on defining these functions mu ij's. Then using these functions and the Lyapunov candidates, we define these sets omega ij's. And finally, we define the switching signals depending upon whether the system states are in the interior of these sets or on the boundary of these sets. So I'm not going to present all the details of how the switching law works, but the most important thing to note here is that this is the exact same switching law designed in this paper, where the authors show that under this switching law, the equilibrium point is asymptotically stable. So the only thing that we add on top of their design is introducing a finite time stable mode, and that this finite time stable mode remains active long enough. And we show that under the same switching law, the equilibrium point is actually finite time stable. So as an application of our proposed method, we work with a switch linear system where all the matrices A, B, and C are allowed to switch. And we assume that there's only one modes out of all the possible modes in which the system matrices switch, which is both observable and controllable. All the other modes are either uncontrollable or unobservable or both. So the strategy for stabilizing the system trajectories using an output feedback for the switch linear system is to design a finite time stabilizing observer, and then using the estimated states to design a finite time stabilizing control. So this is what we do in the simulation example. We again consider a switch linear system, and we consider there are a total of 4 modes, out of which modes 1 and 3 are uncontrollable. So and modes 1 and 2 are unobservable. And only mode 4 is both observable and controllable. So what we do is we design a finite time stabilizing observer first to estimate the system states, because only part of the states are available as the measurements, and then use those estimated states to design a controller that stabilizes the system trajectory to the origin within a finite amount of time. So this is how the simulation results look like. On top left, you can see the evolution of system trajectories, and it can be observed that the system trajectories indeed converge to finite time to the equilibrium point within a finite amount of time. And this finite time convergence nature can be observed from the superlinear convergence that we observe on this log graph. And asymptotic or exponential convergence would have a linear convergence. And as we can see that there is a downward trend, it means that the convergence is happening within a finite amount of time. Similar thing can be observed for the observation error. So the error between the estimated states and the actual states, they also converge to 0 within a finite amount of time. The figure on the top, on the below left, shows the switching signal that was used for this simulation. And as you can see, the system goes into the fourth mode, which is both controllable and observable, but it also switches to all the other three modes, which are either uncontrollable or unobservable, and thus resulting into unstable behavior, which can also be seen from the figures above, that the system trajectories go away from the origin for a small amount of time, or the errors increase for a small amount of time, which means that the system was indeed evolving under unstable modes. Finally, to see how much time the system actually takes to converge to the origin, we performed the simulations for 500 different initial conditions, and we compared the actual time of convergence with the upper bound given by a gamma function that was used in the theorem statement. And we found out that the actual time of convergence is always much lower than the gamma function computed in theory in the paper. So the system actually achieves finite time stability in a much lower time than predicted by our conservative bound in the paper. So with that, I'll conclude my talk here. So we studied finite time stability of a class of switch system, allowing unstable modes to be present. We also designed a switching law guaranteeing that the system would achieve finite time stability. And finally, as an application, we designed a finite time stabilizing output feedback for linear switch system where only one of the modes is both controllable and observable. In future, we would like to utilize this framework to design switch control laws for systems where switching is necessary and which are under temporal constraints, meaning that the system trajectories are required to complete a sequence of tasks in a given amount of time. Thank you for your attention, and I'm